us to see your face or whatever, you just should shut off your face from Teams, and that's enough. So I will not ask you to make some sort of private confidence, whatever. I don't think it is fair enough for us. But okay, so let us start, which is the motivation for me to share with you this information on computational thermodynamics at the basic level. I think that there are sort of specific scientific communities that are using, they are called Calfadians, and they use Calfad software very well, and they are very expert in anything. I'm basically a user, so I was thinking today, like when you know how to ride your bicycle, well, it's not so difficult. So if I know how to ride it, I think you will. Maybe just today, maybe in some days, but I think today you will manage to do. But then there are some details that are important as well. One important point that I should be neutral enough on that is the availability of databases for calculation of phase diagrams, so computational thermodynamics. Of course, there are excellent scientists like Stefano Curtarolo, who is listening to us now, that do provide fundamental data from simulations at a very good level. But most of the data we have nowadays is based on experimental work. So experimental work on computational thermodynamics of alloys is a tough activity that takes months and years as well. So we will try to understand now which is the difference between an ideal phase diagram, in a way, or a more complex real-world phase diagram. This is basically one of the aims of this course. So I want you to get that either you are using your own, so an open database that you have developed, or you are using with sharing with other people, with colleagues. Either you get something which is commercially available, and I think they are very good. The only problem is that they are expensive, and in a way you don't know what it is inside. So one point it is that it is expensive, okay, and the other point it is that you don't know really what it is inside, because if the company, there are several commercial companies that are selling both computer programs like this one called Pandat, but of course there is a wealth of other programs as well. And also there are thermodynamic or even kinetic databases. Nothing against it, but it is difficult to make one database talk with another. And so I think using open database and open databases in general can be helpful, okay? So now it's some 20 persons I get. Can you see my screen? Please say yes, no, or what, because this is important.
Yes.
Yes, we can.
Okay.
Yes.
Yes. Okay.
Yes.
So I have now. Please, if there is not a lot of noise around you, please turn on your microphones. We can, and then if you have something to say or comment, or you can say this, because we are not too many. 20 persons is okay. So let us start with this software. I assume that you have your software on your own PC. Please tell how many do not have. You can tell me. You can take no. So I don't see you. I can hear you or no. So if no one has done it, please do it again. How many no I can hear? Seems this is not a no, but it's okay anyway. I will not turn off your microphones as well. So let us assume that you have downloaded not only the program, but you have downloaded also the zip file from what I sent you in my email. So I have zipped a file. The name of the file, it's something that goes with one, MCC. And so now you have it. So let us go into Pandat and open this one pan phase diagram, okay? And we create the most simple. There are several modules. You can do optimization of thermodynamic databases. You can do precipitation simulation. You can make some phase field simulation. You can play with diffusion and with solidification. Basically, in this course, if there is no any objection about it, we will use just the basic of CalFAD method, phase diagram calculations, and trying to exploit in some real world situations. So let us create this one, and then let us load a database. Let us load any of them, but it could be something, this one, copper, silver, and zirconium. Can you load it? Please say yes, no, or what?
Yes.
Yes.
Okay. Someone says no, it is important as well. Okay. So this is a recent paper, which has been available since, I think, 1 month. I will please select for the moment silver and copper, like that one. We will do a binary phase diagram like that. And then click in this small icon, which is section calculation. Can you see it on the top of the menu, just below pan precipitation, which is not? It is just a pan phase diagram. Can you see it? If everything goes right, you will see something like that. Probably you will not see weight percent, but you will see something different. If you see something different, so mole percent, go into the options. Select Celsius, and select, instead of mole percent or mole fraction, select weight percent. Normally, I'm an engineer, I'm thinking about weight percent. Of course, you are free to think about atom moles, whatever, but normally I will use these units, okay? Please say okay. Please say okay, or say no, I am not getting the menu, or it's a mess, you are not explaining. So once you have selected it, we see a menu with different values. So this is just the top temperature, and this is the composition. It will vary from 100% silver up to 100% copper. Let's see the results, and then we will make some comments as well. Okay? All right? Anyone is in any trouble? Anyone is okay with that?
Okay.
Yeah, okay?
That's okay.
Would you like to click with your mouse on the right button of your mouse and select label? So with label, right mouse and then click, you will select the phases you would like to. Can you do that?
Yes.
Right mouse,
Yes.
click on, okay? Well, it's quite good. So we will have different properties and menus, but we have done our first binary phase diagram using, I suppose, good data from recent publications. So we have a ternary data, so we can use up to 3 components. So how about then selecting database, select component, instead of using silver and copper, we will use silver and zirconium, like that. So we have now silver and zirconium, and see what's going on. You have seen that this phase diagram is rather simple. We will see which is the behavior in this other case. Let us click again in this icon. And let us see what's going on with it. The situation is rather more complicated. One silver and copper, and one silver and zirconium label. Again, we do with label, right mouse, and we see where it is possible. Single phases like liquid, and single phases like this FCC and ACP. We see that the situation is rather complicated. Are you done with us with this? You are okay?
Yeah.
Yeah.
So good.
Anyone which is not good, please. We will just finish it with then. Of course, we should try to start with what we have left: copper and zirconium. Selecting again database, select components, and then we will do copper and zirconium. So we do this one. So again, a section calculation. And we see that also in this case, the situation is rather more complicated with several phases inside our phase diagram, quite a lot of them. Okay, so we have done the first three phase diagrams. Our data are based on a thermodynamic database. We will open this file, which is a text file. Open file, and we will see where it is. It's there. So file, open, and you should have in the unzipped zip file, you should have in the same database you have loaded. Now you are opening with the text editor. Sorry for going to. So open file, okay? So you can open anything like a text or the text file, it is a text file. But even the databases are text files that we give them some special names like we have done, TDB, which means thermodynamic database. And this is the case of the database we have just used. So, which is the structure? So these are comments. With this dollar brand is just a comment. So I put here the dollar brand to remember myself where the data have been taken. They have been taken with this paper, Calfad modeling of phase equilibrium of the copper, silver, zirconium system. And this is the DOI, so you can reach the paper. But I think you have this PDF file for those who don't have access to Science Direct or what else. In their university library, you can reach it because we will work on that. So, which is the structure of a thermodynamic database? You will have the declaration of your elements and of the thermodynamic properties of your elements, and just very rough on that. So if you will have a so-called Calfanian, he will kill me immediately, but never mind, we are in. So, and then the description of thermodynamic phases, like which are inside, like liquid, FCC A1, BCC A2, ACP A3. And so these are input parameters that you are generating from the the one you need. Building a thermodynamic database is a complex activity. I am not really producing data to and building my own databases. Rather, I am adapting already produced single databases or single data that are available to anyone in the net or in the scientific literature. So, should I stop? And any question for the moment, or just yes, it's a mess, I could not open the program, or what else? Please just stop me for a while. Please do. Everything is okay?
Well, everything's fine.
For
Okay.
now, that's okay.
Okay, thank you. So let us temporarily interrupt the window there, and let us go. Let us go just on the internet, and I will try to show you where we are collecting those data. So we have seen that in our database. You are still having a look at here. Yes, you are in the Pandat software in the window. Yes.
Currently, yes.
Yes.
Okay, good. Okay, so you have here a lot of parameters. Okay, what I want you to do now, it is this is something that people has been working a lot, and so this is a recent paper by last month on a specific scientific journal, which is CalFat. So, can you produce an ideal phase binary diagram with your Pandat and your data? Yes, you can. How you can? So database, load SGTE for pure elements. Can you do that? Can you see in the database menu, can you see load SGTE for pure elements? Yes, no?
Yeah.
Okay.
Yes.
Can you load them? So we can select again, silver, copper, and zirconium. Okay? So just to make something different, we can tell Panda to do all binary phase diagrams in the database. We have selected, yes, selected components, yes, good. And so we can do here in this menu, pan phase diagram, we can do all binary phase diagrams. Do not select anything for the moment. So you say none, and then you go. Could you produce such a result or no? Or should I go back and avoid pressing quickly any kind of button or clicking quickly on any kind of button? Is it okay for you?
It worked.
Okay.
Can you do it again?
Please. Okay. Database. Please say me yes or no. The one that load SGTE for pure elements. Okay.
Yes.
Database. Select component like you did the first time. Copper, zirconium, and silver. Okay.
Yes. Okay.
You are done. And then you go into pan phase diagram menu, which has inside this section calculation, which you have already done just previously. But you will tell Panda to do all binary phase diagrams. How many binary phase diagrams are if you have 3 elements? Well, just 3. You can tell me then afterwards how many binary phase diagrams you have when you have 10 or 20 components in your database and you want to do binary phase diagrams. We will take time, but we will arrive to this result. So, do you want to see if there is I have done something more than once. So I will try to see what I have in my hands or not, because I have done the calculation twice. So I will create a new workspace, do all the calculation. I want to have some neat, I will close everything. No. And so I have also the opportunity to do, so first I load this one database, the one I would say select components. This was the first database that we have loaded. So we will calculate all binary phase diagrams. Okay, this was the first set of phase diagrams we have generated. Then, again, with the second step, we select the components that we would like, the same ones, from the SGTE database, and we combine them in the ideal solution situation. What does it mean? It does mean that there are no interaction between elements apart ideal solutions. What does it mean from a practical point of view? So this is the idealization of your situation, and we can copy this data. Are you okay with that, or should I go back, stop and go back, whatever? Yes, no? Can I suggest you to copy data with this comment? So we are in the silver, copper, ideal, SGTE data, ideal or SGTE for me will be the same, copy data, and then we will paste in the same binary phase diagram. Am I correct? Copy data.
Sorry, we cannot see your screen.
This is rather important. Please interrupt me immediately if you cannot see my screen. So my question is, do you have this one with labels maybe, and this one, or no?
Yes.
Yes.
Okay.
Yes.
Okay. Okay. Can you go in this one, which is the ideal phase diagram made using Pandan and SGTE database, copy data there? Can you see it? Copy data.
Yeah.
Okay.
And then we will paste them on, would say, the real or correct phase diagram, phase data. So you can see the difference. In red, there will be the ideal phase diagram. And then in blue, the real phase diagram. The situation is different, totally different, I would say, for this one and also for the other situation. So this is silver and zirconium copy data. And we will silver and zirconium paste the data. We see there is something that resembles the real blue data in the ideal phase diagram, but not that much as well. And then we will go in copper and zirconium copy data, and can you see the difference between an ideal, which is in red, phase diagram, and a real world phase diagram? So there are many, many more intermetallic compounds, and there are many, many more solid solutions. And also the liquidous curve there is completely different in this, and also all the other situation that we have been calculating the situation. So what is computational thermodynamics based. Nowadays, in the future it will be different. But nowadays, computational thermodynamics is based at least on one quite well recognized situation, that we can assign thermodynamic properties of the elements from room temperature, I stress room temperature, up to high temperatures in one way. Okay, so this is what it is available. So I will now interrupt for a while. No, this one, no. I will now try to interrupt my screen sharing, and I will show you how the data are collected. So interrupt it, and I will share the screen now. So you can see my email on the moment, or we can look at, so we've been speaking about SGTE database. So scientific group Thermodata Europe, and this is a sort of company, but there was original paper from Dinsdale, which is available here, for instance. So researchers from all over the world, practically speaking, and using all the kind of softwares, that they agreed to give specific values to pure elements, to give them pure elements, their thermodynamic function. So at least nearly everyone, and I will say a few words, agrees that for the moment we can assign to those elements the thermodynamic properties that they have. CALFAD is a little bit tricky, actually, because you should assign thermodynamic properties to the elements, and that's okay, you can measure them. But you should also assign thermodynamic properties to allotropes which are not stable, at least on temperature or pressures that you have. Which means that on a practical ground, let us again use our, you can have several allotropes that you should take into considerations when you want to build binary or ternary phase diagrams. It is important because phase stabilization is done by temperature, by pressure stabilization or destabilization, but of course by alloying elements as well. So you can have some phases which are most of the time unstable in most of the conditions, which are stabilized by other elements. We will see its usefulness. Meanwhile, we will go with other road. So if you want to have unary, so elements, thermodynamic properties with PANDAT, but you can have with thermocalc, with open CALFAD, whatever, it will be always the same. And you will find those data embedded in your own software, but basically speaking, it will be file open. Let's see if they will be always like this one. So you will find somewhere, even in your own free commercial trial version of your software. We are using a specific software, and it is important to get that computational thermodynamics is not just the one things we are doing with this software, but it is useful to use a tool. Otherwise, you are just using theoretical words. So how are you? Can we do something more? Can we go back to our copper zirconium? So you can save your data. We will save a workspace like that. We will uno, 101. You can give any kind of number, or it is just so you can save all your open files in there, and then you will see section calculations or what else. Okay, can you do that work in save current workspace? Can you see my window? First question.
Yes.
Okay. So can you select their file, save current workspace as, and then I have call it 101, but you can give any number, it's not important. So from there, when you restart, you will create a new workspace like this one, pan phase diagram, and then you will be able to open a workspace, which will be this one, and it will reopen all the calculations that you have seen. You can open, again, open workspace 101 and this extension for Pandat. You can open the graph, but the graph typically is not enough. You can, are you good with that? Can you open your own, say the workspace 101 or not?
Yeah.
Can you do it, all of you?
Yes.
Yes.
Yeah, thank you. So you can open the table, which will contain all the information we have produced. So you will have a table with temperature, composition, phase names as well. And then you will have a lot of more information of what, including free energy. That's all the CalFat databases, they work on free energy global minimization. I am not the good person to explain all details of this. I believe in that. I think he can explain them in a separate course, but here I want you to ride a bicycle, okay? So you can run this tool and you can produce results. This is the task that I proposed to myself. We will not have time in 10 meetings to discuss about theory, but we will face real situations. For this one, you need to do and need to know something more. Of course, if you want, you can export, and if you have Excel, that not everyone likes, you can export your, can you see this one? It's Excel file? Yes, no?
Yes.
Yes.
So if you select this, so we have now an Excel file with those data. Let us see if it works or not. We can use the first two columns and produce this one, which you will imagine, which is just our phase diagram, but shifted, rotated 90 degrees. Is it okay? Just to give you an idea. We will not use a lot of binary phase diagrams in Excel, but it is important that you can export to Excel or any kind of other software. With my students, I used to work with a MATLAB-like software to export curves. Are you okay with it? You can close this example. And well, you have seen that we have different menus. And let us again create a new workspace and do something relatively simple. So database, again, we will produce a binary phase diagram using, for instance, copper zirconium. So load a thermodynamic database. It is the zipped or unzipped file that you have, again, with this copper, silver, and zirconium. select components, we will select only copper and zirconium as well. So I will make a binary phase diagram, but I want to have some special contour lines on this binary phase diagram for some reasons that are related to, I want to see what's going on. So options, there. We have exploited them for changing to wave composition. Then we will do this special choice, which is contour lines. And with contour lines, we click there, we add, and I want to see which is the liquid phase fraction. I will start 0.2, stopping at 0.8, going with steps 0.2. And let us see what's going on. Did you reproduce such a result or not?
Professor
Yes.
Fabio,
Yeah?
I lost it. This last step. Could you repeat, please?
Yeah. Okay. So database, load it, and then you load the copper, silver, and zirconium that we have already done. Okay? This is okay for you?
Okay.
Okay. Then when you are doing this one, section calculation, this small icon there,
Okay.
you will do the same thing we have done before, but you will select contour lines. Can you see
Okay.
contour lines?
Yeah, I saw it.
Okay. You click on there, and once you have a set contour lines menu, you will add this one, F.
Okay.
It will go on the right window there, add. And then you should specify that you want to see liquid phase.
Okay.
Done? Are you done?
I'm writing Ricket. Okay. Yeah, done.
Okay. Then you
Yeah.
press it and you will obtain it. Okay.
Okay.
Any other remark, observation, problems, troubles while we are waiting?
Thank you.
Okay. Any other comment, problem, trouble? So let us go on the red lines, which are the contour liquid phase lines, and go with the mouse and go with F2. You go with the mouse on the line, and then you will see the possibility to press F2. Then you will add the label. So this is sorry, I switched to the wrong window. There was something that went wrong, so I should go back. I hope it didn't not happen to you.
It happened to me.
You as well. You know, you can never complain when you have a free but it should be okay. Normally it is. So create a new workspace, blah, 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 blah. Database. And then I hope it will not happen once again. And then contour lines, and then this, and then this. Otherwise, I will. Okay, so I will go again and hope that everything will go in the right direction. So go there, press in order to obtain the amount of phase. So this is 1, so, and this is 0. you are not using percent, but you are using from 0 to 1. So liquid phase here, it is 1 or 100%. Liquid phase here, it is 0 or 0%. We can do the same game here, here, and here. We can do and see the different situation looking at solidification curves in this program. Solidification curves, for the moment, we will use the equilibrium properties. So we will just run we'll say a simple simulation, assuming that we have the same rules, so just the thermodynamic rules in solidification like we have in this phase diagram. So we are clicking here, solidification simulation. Let us assume that we want to have, just for teaching purposes, 95% copper and 5% zirconium. And we will select, in our course, we will chiefly select this one, non-equilibrium, so Scheil rule. But as long as we are starting, we will just follow the equilibrium phase diagram. So we will use the lever rule. And we will see what's happening. Everyone is good with that? Or should I go back? We've been using this icon. This is a very small ladle casting a metal. And we have done solidification simulation. We have selected a composition. You can choose the one you would like, but I have selected 95% copper and 5% zirconium. And then we have chosen not Scheil rule, but equilibrium lever rule, and we have done it. I will do it once again. Or I will no, because then is it okay for you? Yes,
Yes.
no? Okay.
Yes.
So we have basically introduced, very simply, section calculation, this solidification simulation, basically. How about calculating the liquid surface of our ternary system? It could be okay. Let us see if it will work or not. So let us do a very, maybe it's not correct, totally stupid thing. So we will work with this typically phase projection, and we will use just two components. And so we will see what I am doing here. Here I have projected the liquidus temperature in copper and zirconium. You will tell me, yes, Prof, you are speaking about doing the liquidus surface in a ternary system, but actually we are seeing a binary system. Yes, this is the projection of the liquidus. You can do this one for copper zirconium, for copper silver, and for silver zirconium. Now we do the real, so this is the liquidus temperature, okay? Of course, if we want to go, we can extract data, whatever. But for the moment, I want you to press this to select components, add silver, then we have really a ternary system, and then do the phase projection. We want to calculate the isotherms, and so we don't have just a curve like in binary system, but we will have a surface because we have a ternary system. It will take longer. Are you okay with that, or should I go back while waiting?
Working.
Okay.
Okay.
Okay. While we are waiting for the software, for those who will have the time to do this. So for sure, not the colleagues, but it will depend on how many tasks you have in this ongoing week. I suggest that it would be nice to compare your own results with this recent scientific paper and see whether you are producing useful or not data your own. Of course, you are getting their data. Can you see this one? So you have this ternary phase diagram, typically. You can still shown there. You can add, instead of phase fraction composition, you can add temperature. Most of you will have not these larger characters, but you will have smaller characters, okay? View, options, and select in the graph settings, you can select the legend. I have selected sans serif 16. You can do the same, because I think you have something like 8, so the characters are smaller. I don't think it's big troubles, but you can do there. View, options, okay? Then you can change the axis, the timelines, whatever. But this is important. If you want to have some graph that are readable, the text and the legend, they should be around 16 points character, normal, whatever. It could be okay. Let us go back to our liquid surface. You can see from this perspective. So you are just seeing, normally I tell my students, it's like having a view from 3 mountains, silver, copper, and zirconium. So you are on somewhere high in the skyline from an airplane, and you can see all the peaks and the valleys that you want to see. It's not so easy to visualize in such a way. Sometimes it's a little bit better to visualize it in a ternary in 3D. Yeah, this ternary information. But we will not use a lot ternary phase diagrams. It could be interesting if you want to compare other results. So now we are seeing our 3 mountains, so our 3 elements from the top, and we can see a specific surface. Of course, we could have selected other phases. So we could have selected, for instance, FCC, whatever, but it would be have a little bit more complicated. So this is okay. In your plot, you can, then we will see if it will be possible, it is possible, to shift from this traditional ternary phase diagram system to something simpler. This we will see. For the moment, we don't need it, but we could be interested to do isotherms sections. So you can do in such a way, you can do isothermal sections there. You can do quite easily. I want to see them from 500 basically to 700. Number of steps, not that many. Select 3 steps, otherwise it will take too long. Can you do that? So pan phase diagram, and then no, and then select 3 components. While the software is working. you should have this PDF in the zip file I have provided to you. Do you have it? I think you can extract it. So, which is the possible activity that you can do with these data? You should try to read this paper superficially, and you will understand the amount of work that has been done just for this small ternary system. You will see the binary phase diagrams over there. You can calculate them and you can compare them. Then you will be able not to reproduce X-ray diffraction, actually, but it will be possible for you to do the isothermal sections over there with this one, and this one. So you can compare this figure with what's going there. And you will be able as well, you are able as well to do some child simulations, at least for the liquid there. Okay? Here are the supplementary data, which is the TDB file that I have provided to you. Any possible need, discussion, whatever. For the moment, I think the very basic first meeting information is fine, in order also to let you understand whether this course will be useful for you or not. This can be discussed in. So let us stop and let me see how many people is participating now. Yes, it's some 20 persons as well. So again, please turn on your microphone because I want to hear from you the feedback. This kind of approach, is it useful or not for you? This is the first question that I want to ask. So if you ever have done something like it is okay, but if you have not done it before, I think it is worth, because whenever you have a multi-component database, you will be able to play this game. But you will tell me, yes, professor, we have only the 3 components software. Yes, you have the only 3 component software, but as long as I can work out more complex systems, because I have the commercial license, I can work and produce other results with much more complex situations. Basically, what we will try to work, we will basically work on the zone, which includes the primary solidification, in order to do some exercises and some examples about it. Again, if you have time and you want to send me some of the results, you can produce a presentation, you can produce whatever. It will be useful for you. Why? Because if we go on, it's difficult without a little bit of your own exercise. It will be always like that. You will not see a lot of PowerPoints. I always produce PowerPoint that I don't show them. And so we will go in such a way. Please, Roberto, you're Roberto, yes. Please,
hello.
you ask your, yeah, how are you?
Fine. Hello, Fabio and everyone. And thank you for your assistance for this very interesting utilization of the CalFAT software. I have a question. Besides to work with the pure elements, it's possible to work with the oxides like silicon, alumina, to build the binary diagrams?
Okay, Roberto, it all depends on the quality of your thermodynamic databases you have. My impression is that Pandat is very good to work with elements or with metallic alloys. and there are less possibilities in my mind because of the models related to them. So we are just doing a basic introduction, and of course then you can, if you want to work with inclusions, for instance, or even with, if you're working with steels, with nitrides, with other phases, it could be used. But I think that for the moment, we are just trying to fancy which is the possible use of any CalFAT database and any open CalFAT database. Of course, you can buy Thermocalc, you can buy even Pandat, you can buy, for those who are in Canada, or use FactSage as well. They're excellent commercial software, and you can use them professionally, which is the problem. Normally, the problem is that they are not very cheap, but this is not a problem. Maybe your organization is able to provide them. The big problem is that it is difficult to compare data from different works and different researchers at an academic or industrial field. In my opinion, but this is just my opinion, as for steel, the databases with oxides and software, it is possible more to use with Thermocalc. Unfortunately, I'm much more an user of Pandat than Thermocalc, but I think something that can be proposed. My idea is that people, especially people like me, that I'm nearly 60, we should try to use as much as possible basic information and putting it together. Because in the future, what's going on in the future? Let us imagine that there is this industry 4.0 activities going on. Well, I fancy that in the future, it will be this thermodynamic data that are provided by people doing complex physical simulation like Stefano Curtarolo is doing, but we can put them together, those data, we can put that together from data, as for steel, which are in our steelmaking plant. Why? Well, let us consider, for instance, continuous casting. Continuous casting nowadays, instrumented, is providing a lot of information. It can act like a sort of calorimeter in the future, that it can provide you data, and then you can modify your own data, your own databases. And then you can do something which is useful at an industrial standpoint. For the moment, I believe that this is the future. Of course, most of the casting in simulation softwares, for instance, they have inside their own API, application software interface, that is using some CalFA data. So you have data that are exploited to that. This course is just basically an idea of what's going on this specific topic, in order to understand that if you want to understand something more about CalFAT, you don't need necessarily to buy a software. Then you can buy it or use an open software or whatever. But the beginning, I think it's okay. As for oxide systems, I will ask also Bo Sunman, who's a friend, and what's going on specific oxide systems. I think that there are some possibilities to do in the future, but for the moment, it is difficult to link one to the other. Okay?
Many thanks, Fabio, for your
thank you to you. Any other question from you, apart from Simon? Yes?
Yes. Hi, Fabio. Can you hear me?
Yes, I can hear you.
Okay, perfect. I have a question. Is it possible to using the software to predict the spin order decomposition and miscibility gaps?
Yeah, it is possible. Yes, it is possible. It depends on your specific system. You can do a lot of games from the point of view of thermodynamics. You can do most of the things you would like to. Yeah.
But so it's already like built in, so to speak, in the software, or you have to do something special?
No, you have to play your own games, but I think it is possible, and we can work out some possibilities in the near future if you would like, or we can do something feasible for you. You have any specific system interest, because it is important to identify which are the systems of interest. In
Well,
my
yeah, I was
Yeah.
just thinking, but even the example you did, like the copper zirconium,
yeah.
to do it.
Okay.
Okay, thank you.
If you want, Simon, please send me your details at metallurgia23@gmail.com in order to inform you, because you got I didn't get your registration, so I would just be pleased to have your contacts. Okay.
Yes. Thank you so much.
It's okay. Any other question, suggestion, problem, whatever? I think I can leave you. It's 4:30. So we will meet again next week at the same time. Please email me if you have any question, problem, whatever difficulty, please let me know, okay? To understand whether these meetings are useful or not for you. It is important to understand it, okay?
Okay, thank you, Professor Fabio.
Okay,
Yes.
thank you, Fabio.
Thank you. Have a
Thank
nice day,
you.
all of you. Bye.
Thank you.
Bye.
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 Thank you very much.
Thank you
Ciao,
very
Benjamin.
much.
Bye bye.